Hi everyone, let's continue with another example that has a numerator with a higher degree than the denominator. So I'm looking at this and I'm seeing that the numerator is cubic and the denominator is quadratic. And again, don't forget that it doesn't actually matter which term comes first, it's the highest power. So these could be written in different orders and it would still be third degree over second degree. So when we have this going on, we're going to need to do a couple of things. We still need to try and factor. That's what gives us our local behavior, our wholes, our x-intercepts, our vertical asymptotes. But we'll also need some long division to help us figure out our global behavior. So if I'm going to factor first, looking at the numerator, I see a common factor of 2 and x. So if I divide a 2x out of everything, these 2's are gone completely, and I'm left with a 6 at the end, and then I've divided out a single x, so there's an x squared minus an x minus a 6. In the denominator, I have a difference of squares, x squared minus 2 squared, so this will be an x plus 2, x minus 2. And then I can do a little better in the top. I'm going to get an x, and then I need factors of -6 that add up to -1. So I'll choose -3 and +2 for that one. Okay, so I got it factored, and something that jumps out at me right away is that I can cancel an x plus 2. So starting my list for local behavior, I will want zeros, wholes, vertical asymptotes in whatever order. I'm going to have a whole at -2. So let's continue just a little bit further with this, and then we'll work on the long division part. What I'm saying is that the graph of the original function will be identical to this new simpler function as long as I remember to force a discontinuity at x equals -2. It's called a removable discontinuity because we can cancel it out like that, but it still leaves that hole in the graph. So those holes are removable discontinuities. Okay, so one thing that we want to be able to do is say the y-coordinate of our hole. And remember, to get the y-coordinate of your hole, you're going to go to this simplified equation where we've kind of self-imposed a discontinuity at -2 and say, okay, but I can actually plug the -2 in even knowing that it's going to be a hole in the graph just to get the y value of the hole. So I get 2 times -2. And then I get -2 minus 3, so -5. And on the bottom I have -2 minus 2, so another -4. So it looks like I'm getting -2, -5. So you do want to be able to find the y value of those removable discontinuities. And basically what we're saying is you can't actually get the point -2, -5, but you can get infinitely close to that. So you can get -1.99999, and then your y will be very, very close to -5. So that single point is missing, but everything close to it is there. For zeros, now that I've canceled that factor out, I can look at my numerator and I can say those are 2 factors. And the first is 2x is 0 when x is 0. And x minus 3 is 0 when x is 3. So those will be my x-intercepts. And then last we need vertical asymptote, which comes from the denominator equaling 0. And again, if the numerator also equals 0, like right here, that actually just leaves a hole in the graph, not an asymptote. But when the bottom gets really, really small and the top doesn't, dividing by tiny numbers makes big numbers. So it's the difference between dividing a tiny number by the exact same tiny number and getting 1 versus dividing whatever this is close to, not a tiny, tiny number, by something really tiny and getting a big answer. So I will have a vertical asymptote when x equals 2. And it's very deliberate that zeros and wholes look like points. They are points. Vertical asymptote does not look like a point. It's a vertical line, right? So that's why it's written as an equation. Okay, for our global behavior, we're going to have to do a little bit more work. So we want the global stuff as well. And basically, now that I've simplified, I can see that I still have something that looks like a rational function. It's still a fraction, and the numerator is still bigger than the denominator. So I'm expecting a slant asymptote here. Specifically, the numerator is quadratic and the denominator is first degree. So that being 1 degree apart is what tells me it'll be a slant. Just to point it out, we won't do these, but if your numerator was 4th degree and your denominator was 2nd degree, for example, those are 2 apart. So your global behavior would look like a quadratic. And if they were 3 apart, it would look like a cubic. So it's just the difference between the degree at the top and the bottom that's actually determining this. Okay, so we can do our long division either by going all the way back to this original function, or just to make things a little easier, we could snag this new function and say, well, let's just do the simpler problem and divide x minus 2 into 2x squared minus 6x. And it's not so confusing when you're missing a term at the end, but I'm still just going to put that plus 0 to leave myself a space. Okay, so first we need to make the 2x squared and the x match up. So what do I need to multiply x by to get 2x squared? And the answer is a 2x. And then again, you're multiplying both of these, so we'll have a 2x squared minus a 4x. And then don't forget that we're subtracting. Number one mistake I see is that people don't switch that middle sign. So just be careful. 2x squared minus 2x squared is 0. That should always happen if you're doing this correctly. Negative 6x plus 4x is negative 2x. And then again, this is just kind of lining things up. There's a plus 0 there. We next need to make the negative 2x and the x match. So to make the x into a negative 2x, we multiply by negative 2. And again, don't forget to multiply the whole thing. So we get a negative 2x plus 4. And then we subtract. The negative 2x's go away. Don't forget that this is 0 minus 4. So we have a remainder of negative 4. So what this means, here I'm going to sneak it in right here, is that another version of this is that our original rational function q is equal to 2x minus 2 minus 4 over x minus 2. And I'm running out of room, but that would still have that domain restriction as long as we don't let x equal negative 2. But it's okay that I kind of scrunch that, because what really matters here, we're only using this for our global behavior. And what we care about is that as x gets really, really big, this fraction at the end gets tiny. It basically it becomes negligible. So what's going to dominate the behavior of the function at that point is this line, 2x minus 2. So if we start to draw our graph, we say minus 2, and then it has a slope of 2, so it'll cross at 1. Y equals 2x minus 2. There we go. If we draw that in, what we know is that we should have an arrow really close to that on the far end. So we don't get very far out of the left and right side just because of the way I drew this. But as we get further and further to the left and right, we'll get closer and closer to that line. We also know that we have a vertical asymptote at x equals 2. And we know that we have a hole in the graph at negative 2, negative 5. So it would be really nice to figure out whether that hole lies above or below the slant asymptote. And remember, that slant asymptote is just a line. So if I'm interested in what's happening when x equals negative 2 with this line, like where is this point, we can just plug into this equation. 2 times negative 2 minus 2 is negative 6. So the hole in the graph will be above that. The line goes through negative 2, negative 6. The hole is at negative 2, negative 5. And I think I did kind of a terrible job with lining this up with tick marks, but 2, 3, there we go. So say that's negative 6 and that's negative 5. Okay, and I'm just going to label it to be really clear. And if you're not drawing on a grid, do that for me so I know exactly where it is, or make sure you've written exact coordinates somewhere. Okay, last thing, I need my x-intercepts. I know this crosses through 0, 0, and I also know it crosses through 3, 0. So I need to start on the left. My far left isn't super far because I have a slant asymptote, so I'm going to be starting from right here. And the first thing I need to do is to hit that hole in the graph. So I'm actually even going to move this a little further out. I'm going to say this is probably a little above. It hits that hole in the graph. The next piece of local behavior is an x-intercept at 0, 0. Note that everything here is multiplicity 1, so we don't have to worry about any bouncing off or any mirroring on the two sides of the asymptote. It's just going to cross straight through. And then we need to either head up to positive infinity or turn back around and head to negative infinity. And we can't turn back around because we don't have an x-intercept on this side of the vertical asymptote. So this is going to be one of those really wide, stretched out looking hyperbola. Okay, so the asymptote was also multiplicity 1, which means we need to switch from positive y values to negative y values as we cross that. It basically means that this factor right here will change signs at 2. It'll switch from positive to negative, which will force the y value to switch from positive to negative. And then last little bit here, we do have one more piece of local behavior. We have to cross through the axis at 3. And again, I know it's a cross through because everything had powers of 1. And then all that's left is that global behavior. So we're just going to start slanting a little bit as we go. And again, I don't know if you can see this, but personally, it really helps me to be able to kind of visualize how this is related to the parent function. So what we want to imagine here is if we picked up this horizontal asymptote and we tipped it, and again, it's a little different because we're not looking at a line that goes through the origin, but same idea, that basically doesn't affect the vertical asymptote, but it does kind of skew out. It lifts this up. It stretches it up in kind of a funny way. So not that that's like a super official, perfect way to do it, but just to kind of have that visual of this really is still related to the parent function.